All right, so today we're going to talk a little bit about the Michelson Interferometer, and specifically we're going to derive the path difference for the fringes that are created on the viewing screen of the device. So a little bit on the interferometer itself. The premise is that, again, we shoot light from a particular source, and the light will take two different paths to the actual observer, and those paths are actually gonna they could potentially have a path difference between them, which will give rise to constructive or destructive interference. So one of the things we should be aware are the paths, because they're going to be useful in derivation as well. Specifically, one of the paths is, again, the beam here could go straight through the beam splitter, through the compensator, reach mirror 1, get reflected, then bounce back, and reflect off of the outside here of the beam splitter, meaning it only goes through the actual beam splitter once, through the actual glass portion. Now, the other path over here that we could follow is a little bit different. So we're going to actually reflect from the back of the beam splitter, and then we're going to refract over here at the front in a way where we end up heading toward the mirror 2, and then we're going to turn back, reflect again, and go through the beam splitter a second time, but this time we're going to go through it and into the observer. So this time around we have twice the traversing of the beam splitter's, again, glass area. That means, again, that there will be an unwanted phase difference of pi between the two actual beams, regardless of, us wanting it or not. It's going to be there. And to account for that phase difference of pi, we're actually introducing here a compensator for the actual beam that goes and reflects through mirror 1, so that we account for the path difference, again, introduced by the different locations and paths taken by the beams. We account for that with a little bit of a compensator, and therefore we basically eat up that phase difference of pi. Now, all else being equal, again, over here, we would arrive at the observer at an equal path. We wouldn't have a path difference. Now, the thing about the actual setup here is that we do want to induce this path difference. And this path difference, again, we're going to represent on the diagram with an actual variable d. And I want to mention, again, that we control the actual path that our ray takes to mirror 2 with an adjustable micrometer. So we can scroll the micrometer around and change the position again. We can move this mirror back and forth to account, again, for whatever adjustments we want to make to the path difference between the two paths. So we could have the two paths be equal length, or we can change that with the use of the micrometer. Now, suppose, again, that I don't have those paths be equal, and I've introduced a path difference into the system. The compensator, again, will have taken care of the phase, so the only thing we have to worry about for the optical path length is the physical path length, like the actual distance that the rays travel themselves. So over here, we can see that we have labeled on the diagram the path here between the beam splitter and the actual mirror 2. We've labeled it as X. And the path from the beam splitter all the way to mirror 1, we've labeled it as Y. Now, provided, again, we've introduced a path difference, we could take this chunk over here, this Y, and kind of like put it overlaying here with the X to compare the size, and it would look something like this. Your Y difference would be a little bit shorter right now than the X, the residual part, again, being the actual path difference that we've introduced with a micrometer. So that's not going to be, of course, the final path difference that we're going to see with our eye, but it's going to play a role in deriving that. So we got to take note of it. So we've got the basic setup over here, the basic premise down. Now, the next thing I want to do is I want to ask the question, where does the observer see the individual mirrors actually with his eyes, like if your eye is there? For the purpose of simplicity here, what I'm going to do is I'm going to make the eye basically here have a 0 distance from the beam splitter. We're going to put our eye basically right there against the beam splitter itself, just so we don't introduce any more variables that are unwanted for the distance, and they all end up canceling anyways at the end. So we got our eye where the green dot is, and we're looking to see where the mirrors appear. Now that's very simple to see from mirror 2 where it appears, right? We can see over here that our eye is going to pick up the location of mirror 2 right there, right? And if we wanted to represent that in a linear fashion, we could put the actual eye over here. You can call yourself an observer here. And we see that the length of this red line, where your second mirror would be actually appearing, would be a distance again, a physical distance. We're going to color it in over here. It will be a y plus d right now, the actual distance over here. So we got a y plus d right there. And that's where our mirror 2 will appear. So I'll put a little plane over here and rotate it to do the actual mirror and where it will appear. There it is right now. So that's, again, where M2, we're going to call this guy M2, where he would appear to the eye. Now, what if I wanted to see where the mirror 1 appears to the eye? Well, for that one, we have to steer this way, and we see that our mirror 1 right now appears a distance y. But does it appear to the right of our point of view? No. The light here, as you see, appears to be coming straight ahead from the beam splitter. So actually, the distance y that we perceive mirror 1 to be is actually ahead of us. We see a virtual image right now of mirror 1 that would be located right there. So that would be, again, if we want to call it something, I would call this M1 prime because it's a virtual image of the mirror, versus this one over here would just be the regular mirror itself. So we get to see this mirror straight ahead, right, at a distance right now, y. You can see how I've preserved that distance y when I place the virtual image of M1. In the linear fashion, right, that we're trying to construct over here, in the linear scheme of things, that means that that mirror, going to represent it again in blue over here, that mirror would appear to be a little bit closer right now to us, maybe over here, okay? And that distance again is just going to be y. We're going to represent it over here. That distance to that mirror, again, just y. You can see again that the separation between the virtual image of that mirror and the second mirror, this distance is again a mere d right now. That is the residual here. That is the whole difference. And that's pretty much where we see the mirrors lined up right now. So this is beautiful. We got our setup straight. From here now, this is what the mirrors look like to the observer, but that's not what the observer sees. The observer sees the actual source. So we gotta somehow put the source inside this diagram. And for that, we gotta dig a little bit deeper. So I'm gonna simplify now the diagram a little bit over here. Okay, we're gonna simplify it and talk about the actual source, which for the moment is gonna be a point source, and then we're gonna extend to an extended source. If we put the actual point source over here right now, let's see how far it has to travel to get to our eye from each path. So again, the light that comes from mirror 1 right now, let's see. Let's say that this distance to the beam splitter right now is s. Why not? And then the light from the source will continue, as we said, for a distance y, bounce back, and then travel another distance y. So you're already at 2y over here, right? And then it's gonna go back into our eye right there. So, okay, how far is right now mirror 1 from that source physically? We can see that. That's s, and then it has to continue over here another distance y. So that's pretty simple. That's the distance from that mirror. Where would a mirror produce an image of that source based on, reflection theory? It would produce an image an equal distance behind that mirror. So we would see the actual image actually all the way out here. That would be I1 right now. That's where you would see the image. And what is the length of this? That will be exactly S plus Y. So having this right now under our belt, we can go and include it, now that we understand where the image is going to be, we can go and include it to our actual diagram over here. We can go and add that. Just a second as I move things around. And we can add, again, we're going to take the Y plus D over here. This guy, this Y right now, our source would be behind the observer. So we're going to add the little S right there. All right. So this is our little S. And again, the distance, we are, as the observers, we are on the beam splitter. So the distance to the beam splitter, we represented it, if you recall, with S, right? From this diagram right there, we represented that distance as S. All right. So we're going to represent that here as S2. And we can see that as I'm going to reach right now this guy, the distance from the between the source and my mirror is again S plus Y, preserved as is in the original diagram over here, S plus Y. The image again is going to be an additional distance S plus Y behind the blue mirror here. So I can just copy over here these distances as I am on OneNote. Okay, clean this up a little bit. And I'm going to add them behind over here. There they go right now. So my image is going to be on a plane that is exactly out here right now. Okay, that's going to be where I see that little dot, that little S right now. So the total, again, you can see over here the total of the blue line. The total of the blue line is 2S plus 2Y right now. Okay, so we're getting there. Now, what about the red one? Well, we got to figure out the distance of our source to mirror 2 right now on this diagram. So that distance is, again, we have to traverse the distance to the beam splitter, which is the same. We called it S. And then we have to go upstairs all the way to that mirror. And that is the optical distance here. We represented that with X, but I'm going to skip X and call it, again, Y plus D. So the Y plus the actual difference that I've introduced with a micrometer. That is my optical, again, path between source and mirror 2. And then we're going to ask here, where is the image going to form? It's going to form, again, behind mirror 2, all the way out here at a distance S plus Y plus D right now. That's what we're going to get. So how does that look on our diagram? On our linear diagram. We've got over here again that we have to go to the beam splitter, so a distance S to get to the beam splitter right there. And we know that the distance, the rest of it to the mirror 2 is Y plus D. So again, because I'm on OneNote, I can do this very easily. I just copy this right now. Okay, and make sure I tweak it properly. And so the image from mirror 2 is going to be an equivalent distance behind it. So we're going to go all the way, as you can see, out here to actually get the image of S right now from mirror 2. So that's where we are. And we can see right now that the path difference that would be seen by the observer is merely this chunk of length right there, which I think we can determine. So if we see again the sum of all the reds over here, the total would be simply 2S plus 2Y plus D. And if I wanted right now to find the yellow path, I would just take the total, which is the red right now. I would take the total, so 2S plus 2Y plus D, and I would take away the blue, which is the remainder of the path here, right? I would take away the blue and have subtracted here 2S plus 2Y bracketed. So we can see there's a bunch of cancellations here These go away, and then this guy goes away too, only to give us a distance to D. And that would be, again, ideally what happens if the source was, again, a point source. However, our source is not going to be an actual point source. It's going to have some extent. So for this reason, again, we're going to come back into a second part and see how the extent of the source now will change what the path difference will be, what we will have to introduce there to talk about different angles that the beams could be approaching the mirrors. Because when you have an extended source, you could have a beam, not all the beams will go horizontally. You could have a beam that goes like this. And we want to know what is the effect of this theta over here on the path difference that arises all the way out there. So stay tuned for part 2. Don't miss out, and we'll explain what happens from an extended source.